Hello students, in this lecture we will see the concept of stability. See the example of cone shown in the diagram. In the first diagram, that is figure A, it is the stable, cone is stable because its surface is touching on the plane. Okay, so it is stable. In the next, it is neutral. It is neither stable nor unstable. We cannot say that it is stable or unstable. So it is neutral. And in the third, it is unstable because it can fall at any time. Stable system. A linear time invariant system is stable if following conditions are satisfied. First, a bounded input is given to the system. The response of the system is bounded and controllable. See, when we give the bounded input to the control system, if its response is also bounded and it is in our control, then this system is called as stable system. Also, in the absence of the inputs, the output should tend to 0 as the time increases. See, in this diagram, for a stable system, input is bounded, output is also bounded, and also the output tends towards 0. And as you can see, the location of roots for this stable system are in the left half of the S-plane. So the left half of the S-plane is shown here by the shaded area. Unstable system. A linear time invariant system comes under the class of unstable system if the system is excited by a bounded input and response is unbounded. See, when we give the bounded input but if we get the response unbounded, then this type of system is known as unstable system. This means once any input is given, system output goes on increasing and we don't have any control on it. This is shown here. We have given the bounded input but we have no control over the output. The output is unbounded. In this case, the system is said as unstable system. Now see the location of roots for the unstable systems. The roots are in the right half plane of the S-plane for the unstable system as shown by the shaded area. Then critically stable system. When the input is given to the linear time invariant system, for critically stable systems, the output does not go on increasing infinitely, nor does it go to 0 as the time increases. See, we have studied the stable system and unstable system. So, in case of stable system, as time goes on, as time increases, the output tends towards 0. Okay. And in unstable system, the output goes on increasing infinitely. But in case of critically stable system, neither the output go on increasing infinitely nor it go to 0. Okay. The output usually oscillates in a finite range or remains steady at some value. Such systems are not stable as their response does not decay to 0. Neither they are defined as unstable system because their output does not go on increasing infinitely. See here the critically stable system. Input given is bounded input, but the output is non-decaying output. Neither it is going towards 0, neither it is increasing, just it is oscillating. Okay, uh, in positive cycle, then negative, positive, negative, like this it is oscillating. So this type of system is critically stable system, and the location of roots for this critically stable systems are on j omega axis. Okay, so the roots will be imaginary values. Next concept is relative stability. See, the meaning of relative or relativity means when something is compared with the other thing, then we call it as relative. Okay, a system may be absolutely stable, that is, it may have passed through the Routh stability test. Okay, so this Routh stability test we are going to see afterwards. Okay, so when this control system passes this test, then it is called as absolutely stable. As a result of its response decays to 0 under 0 input conditions, and the ratio at which these decay to 0 is important to check the concept of relative stability. So I will give you one example to explain this relative stability. See, when the poles are located when the poles are located far away from the j omega axis in the left half of the S-plane, the response decays to 0 much faster as compared to the poles close to the j omega axis. The more the poles are located far away from j omega axis, the more is the system relatively stable. It means that when the poles of a particular system are near the j omega axis in the left half of the S-plane, then its response decays to 0 faster. Okay, and when they are near, then response is slow. Decay in the response is slow. See here, two systems are given, system A and system B. Now you will understand easily from this example. In system A, response decays slowly and its settling time is more. You can see from the diagram, the response is slow and settling time, that is time to reach the response towards 0, is more. And for the system B, the response decays faster and it settles quickly. Okay, so system B is relatively more stable than system A. Understood? The system in which the response decays faster or settles quickly is the more stable system. Here there is a comparison of the location of the poles for the both systems. For the system A, the poles are having complex conjugates. Okay, so for example, 2 plus j, 2 minus j, or minus 2 plus j, minus 2 minus j, like this. Okay, they are on the negative side, so they will be minus 2 plus j, minus 2 minus j, and suppose the system B is having something like minus 5 plus j and minus 5 minus j, like this. Okay, so they are having conjugates, complex conjugates of each other. So the poles of system A are near to the j omega axis, and as you can observe, the poles of system B are far away from the j omega axis. So the system whose poles are away from the j omega axis is more stable. So like this you can also predict the stability of the system from this pole 0 plot which we have seen earlier. See here, relative stability improves as roots moves away from the j omega axis. Now the roots stability criteria. So let us consider the standard transfer function in which C of s divided by R of s is given by b0 s raised to m plus b1 s raised to m minus 1 plus up to bm divided by a0 s raised to n plus a1 s raised to n minus 1 up to an. In this criteria, the coefficients of denominator are arranged in an array, and that array is known as roots array. Okay, so for arranging the array, for creating the array, we have to take the characteristic equation, that is nothing but the denominator of the transfer function is equated to 0. So that is a0 s raised to n plus a1 s raised to n minus 1 up to an is equal to 0. See how to create the roots array. Consider the coefficients of s raised to n and s raised to n minus 1. So coefficient of s raised to n is a0 and coefficient of s raised to n minus 1 is a1. So for creating the array, you have to create the structure like this, and first you have to write down s powers to the left side of it. So we have written like this: s raised to n, s raised to n minus 1, s raised to n minus 2, s raised to n minus 3 up to s raised to 0. Okay. So once you have written the powers, then you have to write down the coefficients to form the array. See, for example, if the equation is having the terms like s raised to 6, s raised to 5, s raised to 4, s raised to 3, s raised to 2, s raised to 1 and s raised to 0, then you will write at the left side all the s powers, that is s raised to 6, s raised to 5, s raised to 4, s raised to 3, s raised to 2, s raised to 1 and s raised to 0, like this. Then next step is see the coefficients of s raised to n and s raised to n minus 1. In this case, the coefficient of s raised to n is a0 and coefficient of s raised to n minus 1 is a1. So in the first row and first column a0 is written, and in the second row and first column a1 is written. See, a0 and a1 are written here. Then we have to repeat this. So a0, a1, then a2, that is the next coefficient, will come in the first row. Then a3 will come in the second row. Then a4, then a5, then a6, a7, like this. So whatever are the coefficients in the given characteristic equation will be written like this. So you have to write the alternate coefficients in each row. So in the first row, the coefficients are a0, a2, a4, a6, and in the second row a1, a3, a5, a7, etc. Now we have to calculate b1. See, b1 is shown in the different color, blue color, and see how it is calculated. b1 is equal to a1, a2 minus a3, a0. See the arrows shown in red color. B1 is equal to A1 A2 minus A3 into A0 divided by A1. So this is how A1 is calculated. Sorry, B1 is calculated. Next is calculation of B2. So for B2, again see the arrows shown here. B2 is equal to A1 into A4 minus A0 into A5 divided by A1. B3. See arrows again. So you will observe that we have put the first column contents, that is A0 and A1, as constant. Okay. So here also B3 is equal to A1 into A6 minus A0 into A7 divided by A1. Next, C1. So next row. C1 is equal to B3. C1 is equal to B1 into A3 minus B2 into A1 divided by B1. C2 is equal to B1 into A5 minus B3 into A1 divided by B1. So you have to go on like this to calculate the values up to the s raised to 0, and finally you will get the last value, that is an here. So each column will reduce by 1 as we move down the array. Okay, so observe here the first two rows are having 4 columns or 4 values each, but in the third row there are 3 values, fourth row 2 values. Like this each column will reduce by 1 value, okay, as we move down the array, and this process is obtained till the last row is obtained. See what is actually the Roots criteria is. So after forming this roots array, you have to check the first column of the array and it must have the same sign. The necessary and sufficient condition for a system to be stable is all terms in the first column of the roots array must have the same sign. There should not be any sign change in the first column. Okay, what the roots criteria says, all the elements from the first column of the roots array should be having the same sign. Then and then only the system will be stable. So when there are sign changes in the first column of the roots array, then the system is unstable and its roots are in the right half of the S-plane, and the number of sign changes equal the number of roots in the right half plane. So this we will see in the numericals in the next video, but see in the roots array there are two sign changes, plus A1 to minus B1, the sign is changed. Okay, from going from second row to third row, the sign is changed from plus to minus. So this is first sign change. Again going towards to the third row, the sign is changed to minus to plus. So there is second sign change. So totally there are two sign changes. So therefore there will be two roots in the right half plane of the S-plane.